Hi everyone. So yeah, hopefully you have an idea of what ASR is. We've been pretty publicly vocal about it. So yeah, today we are going to talk about a bit about super resolution and how we brought temporal super resolution or temporal upscaling efficiently to mobile. So here's a high-level overview of what the agenda for the talk is. I'll start with quick context. What was the motivation for doing this? So some performance and image quality metrics, because we all love that data as engineers, I guess. And yeah, and after that, I'll give an overview of how do you actually integrate this in your code bases and what our way to market is for ARM-ASR. And finally, I'll focus a bit more on the Vulkan specifics, since we love Vulkan. Vulkan is our main API, and we wanted to make it as simple as possible for developers to use it. So first, why did we decide to create our own temporal app scaler on mobile or optimize an existing solution? So if you take a look at the spectrum, this has been resolved on consoles for a long time already. You have plenty of techniques that work super efficiently on the recent consoles and desktop. But when you go to mobile, your only option up until recently was basically the spatial upscalers. And you can only go as far when it comes to the upscaling radius there without sacrificing the image quality. Now, with higher end games and GPUs becoming way more powerful, people are starting to bring these console level techniques to mobile. So yeah, we thought it was the right time to bring temporal upscaling and allow developers to lower a bit more that source resolution and be more aggressive with the upscaling workflows. So just to give you an idea, with temporal upscalers, you can now go all the way down to rendering your frame at a quarter of the resolution, and then upscale to your native resolution. So that would be doing the work for 25% of your pixels on the frame, and then just upscale to full res without compromising the quality. So with ARM-ASR, we wanted to fill the gaps there, try to cover the areas where spatial upscalers don't reach, and ultimately get the nice power savings, reduce the temperature, and get performance. So at the time, my boss came asking, well, we need to deliver an upscaler. How do we get there? So I had to, ask myself what kind of upscaler we wanted to go for. FSR1 was already a super efficient solution at the time. So I thought, well, let's give it a go with a temporal upscaler. And as I said, try to go a bit further when it comes to the upscaling workflows. Also, turns out temporal solutions are quite complicated in terms of how many stages you have there. You have a lot of intermediate resources, you have history buffers, feedback loops of all kinds. So it could be pretty complicated for developers to integrate that tightly in the engines. So I wanted some delivery mechanism that abstracted developers from all of that. And yeah, there are many vendors. Everyone is trying to push their own upscalers and bring their own use cases. So one of the key goals for me was to try, since we were already contributing to the problem, try to minimize the API fragmentation, try to be as friendly as possible to something that might already exist in the game industry code bases. So I decided to give it a go, follow the lead of AMD and what they've done with FSR2. So if you haven't tried FSR2, it gives really good image quality. It's used everywhere worldwide. It's super popular in the console environment. And yeah, it's a temporal upscaler. So it comes with some requirements in your engine. So you need to jitter your frames, ideally with a Halton sequence. You need to provide motion vectors because it temporarily integrates the signal. So you need to reproject to the previous frame information and somehow deal with ghosting or any kind of artifact that you might encounter. And also you need to compensate for the fact that you're rendering at a lower resolution, but your final image needs to look as if you were rendering at the target resolution. In order to do that, you have to apply a global MIP bias when texturing. Basically, that bias that you can see there. In terms of the inputs and the outputs, we are pretty much the same as FSR2. So you provide your source resolution, jittered, input color, which can be in HDR or tone mapped. The low resolution depth, we support same as FSR2. It can be reversed set, which is fairly common nowadays. We have some flexibility when it comes to the motion vectors. So you can provide the low resolution and jittered motion vectors, but you can also provide dilated motion vectors. And optionally, we have also the concept of the reactive mask. So if you've done anything with upscalers, you know that there are things like translucent particles that don't provide depth information and motion vectors. And without that data, it's pretty complicated to reproject to the previous frame. So we kept this concept of the reactive mask. So the user had some flexibility and an entry point to the upscaler to specify which areas didn't have to use that much history information. And ultimately, the output is your upscale image, which can be in either HDR data or tone mapped. So how does the performance and the image quality look like? Well, let me start with introducing the shader quality preset. If you've used upscalers, you might know that they refer as this quality presets concept, but in reality, most of the time, that just means use this upscaling ratio or this other upscaling ratio. Now, if you are in the console world, your hardware is super stable and the kind of, your target is not as wide as the spectrum that we have to deal with in the Android ecosystem. So I wanted to provide some more scalability there. And so I decided to introduce this concept of the quality presets. So in essence, for us, we have the quality, which is an ultra optimized, micro optimized version of FSR2 without compromising any of the image quality. And then we came with a balanced preset, which gives a pretty nice performance uplift and considerably bandwidth reduction as well. And then we left the door open a bit with the performance preset. It still gives you another uplift. It still gives you some extra bandwidth savings compared to the balanced one, but it's still a bit of a work in progress. So we want to improve this one further and be even more aggressive in the future. To give you a context, we were going to do a lot of optimization work, and when you are optimizing, things can go wrong super quick. You can have regression in the image quality, and if you are creating an upscaler, I don't think regressing the quality of your results is an option. So we were really careful tracking regression and validating in every single one of our optimizations. As I said, for the quality preset, losing quality was unacceptable for me. I was going to do some quality performance trade-offs for the other presets, but I wanted to make sure and guarantee that all the trade-offs were always worth it. So these are well-known metrics used when it comes to evaluating image quality. We have the PSNR, SSIM, TPSNR, which is like a temporal equivalent of PSNR, and the STR red error. And yeah, so you use these metrics for evaluating different concepts from temporal stability or how good of a work your upscaler is doing at getting the job done of upscaling, or simmering and any other kind of temporal artifacts in general. So hopefully the numbers are not too, okay, yeah. So numbers look good. So this was the starting point. This is how FSR2 looks like on a fairly recent mobile phone with Immortalis G720, which is like our last year GPU. And as you can see, the overall duration of the GPU work related to FSR2 is pretty high for your typical budget on Android. And looking at the bandwidth, that's definitely out of the budget that you have in a frame on mobile as well. So we needed to do something about both of these. This was definitely not in a production state. It's a really good upscaler when it comes to the image quality, but on mobile, it wasn't designed or nor optimized for mobile. So, okay, let's get things moving. We started with the image quality preset, and here we were focusing mostly on the non-intrusive optimizations. As I said, any kind of micro optimization that we could do without sacrificing quality. And I think we did a pretty good job. As you can see on the chart, top right of the slide, we roughly get 100% image quality match compared to FSR2. As a matter of fact, ASR is slightly above FSR2 in this chart for some reason. And in the process, in terms of the duration on this Immortalis G720 device, we get well under 3 milliseconds, although the bandwidth is still a bit too high for what I would like, but this is already in a state where you can start considering using it for production in a high-end game. So then we go to the balanced preset. And in this one, we were tweaking a bit more the algorithm, maybe encoding things differently, using cheaper kernels and things like that, encoding the information differently. And we still managed to get roughly similar image quality compared to the quality preset. We get a really nice performance uplift. As you can see, now we can go well below 2 milliseconds, depending on your configuration, your upscaling ratio. And the bandwidth is starting to look promising. Like I think the balance preset now, if you have some high-end content, you can just use it. And then lastly, we had the performance preset. So once again, we didn't want to be too aggressive and destroy the temporal stability or the quality results. So we tried to not be too aggressive. And now, based on the feedback from the developers, it looks like some developers are happy to go even more, dropping quality a bit further if it comes with some better bandwidth or even performance. And now in terms of duration, the upscaler, gets the thing done, and you are almost not going to have that much of overhead in your frame. So you can get some really nice improvements there. In terms of bandwidth, as you can see, if you use the performance preset with 2x upscaling workflow, using this target resolution in particular, the bandwidth used by the upscaler will go between 41 to 50 megabytes, and this is external bandwidth, excluding any internal, caching and stuff, which is good considering it's pretty good considering the amount of intermediate resources and things that you need to do in a temporal upscaler. Turns out you need a lot of information for the heuristics, for reprojecting and cleaning all these artifacts that usually come. So now, just visual representation, just so you can get that comparison against FSR2. So on the left, you can see the duration of the technique originally and how things have evolved with the quality presets. And on the right, you can see where we started with the bandwidth and where we ended up being with the current state of ASR. So I haven't gone through the optimizations and technical details, but we gave a presentation at GPC in November. So it's all in YouTube. If you are interested in hearing more about the kind of optimizations that we did, feel free to go to YouTube and watch it. And here's some visual materials. Since this is graphics related conference, so I thought, let's play a video and people can see it in action. So this is our internal high-end demo created internally by our content team using Unreal Engine 5 with things like Lumen. You have particles there, you have a dynamic lighting environment, animated foliage, and the kind of things that upscalers struggle with. And as you can see, the quality is good. And if you render at the native resolution, you get 19 FPS in this particular run. If you enable 2x upscaling with ASR, the quality stays the same, but you basically get a 2x performance uplift. And these are some performance data from this demo, different runs. So we were using a target resolution of 720p. And yeah, this particular run, since the content was high-end already, we didn't even try to with the other quality presets. So I just gave it a go with the quality one, and I could easily get 2x performance uplift in this particular environment. And as you can see, similar, like 83% improvement when it comes to the FPS per watt as well. Just to be clear, this is a pretty high-end piece of content with Lumen and ray tracing, so not your typical content, but just so you get an idea of where can you get with super resolution. So now some more details about how you can integrate ASR. As I said, ASR is shaders. There's nothing vendor specific there. You can run it in any platform, any API. We have some developers who have already succeeded at running it with, of course, Vulkan, but also Glass, DX11, DX12, Metal, you call it. Given the temporal nature of the upscaler, we generally recommend people to use the late 2022 devices and onward. And that's because something like TAA just became usable on production around 2021, 2020 generation. So, and temporal upscalers are more complicated. So in order to guarantee that your upscaler can fit within a budget of 4 milliseconds or less, yeah, I think this is first generation where you can start using it on production. Before that, I think it's probably spatial upscaler territory, but rule of thumb, do your profiling, profile your game, get the budget and see whether ASR works for you. Now, at the beginning of the presentation, I was saying about the user experience and the delivery mechanisms. And this has been a big challenge because, yeah, it's a pretty complicated technique. You have multiple stages, you have intermediate resources, you have to manage all of that. You have different shader variants for the different quality presets and all the flexibility you're using, reversed buffer, dilated motion vectors, etc. You have to provide the correct uniforms as well. So just based on this, just delivering the shaders in a GitHub repo wasn't an option. I didn't want to create a problem for developers, so they would have to integrate and recreate the entire algorithm in their engines. Also, Vulkan is our main target, and we will see in a moment. There are challenges associated with Vulkan. It's not a trivial API. So yeah, I wanted to provide a quick delivery mechanism when it comes to the Vulkan side of things. And elephant in the room, maintenance and scalability, of course. I didn't want to burden our final users with, if a new version of the algorithm lands in the future, I didn't want anyone to have to go and refactor the whole thing. So hopefully we could deliver something that provides a transparent experience. So yeah, you already know, but we followed the AMD's lead on this. So our FSR2, well, ARM-ASR is inherits from the original FSR2 in the FidelityFX SDK 1.0. So I didn't like renaming things, but yeah, for things like the FFX, we renamed that to FFX-M to avoid any kind of symbols duplication or conflicts with potential existing integration of the original technique in the code base. So just to wrap things a bit, we extended and optimized a bit, and yeah, did some work in the Vulkan backend, adding all the missing features there. Things like the support for render passes, because now we are using fragment shaders for most of the stages. And yeah, the FFX-M interface can be overridden by the users to provide their tight integration in their engines. So you can do some work there if you want to walk that extra mile and connect things tightly with a render graph, for instance. So you're probably all, or most of you, familiar with how things work, but just in case, this is how you would have your setup in the engine. Somewhere you would have a third party with the code for ARM-ASR, our reference implementation. And then in your engine, you would have some file where you want to connect things with the renderer. So you would start by including these files, the ffxm interface.h and start2.h. If you're using the standalone backend, you might want to include as well the BK header equivalent. And initializing things is pretty straightforward. Just allocate the required memory for your context, fill the FFXM interface with some function pointers for the callbacks there. So this is a lightweight rendering-like interface that the algorithm targets. So you can use this for basically connecting the entire algorithm with your renderer, basically. And finally, you create the context. Same way as you would do with FSR2. We just extended it with a new field for choosing the quality mode. And this is how you select the quality presets. And depending on what you choose here, later on, the algorithm will request the pertinent shader variants for the presets. Same story for upscaling. Every frame, it would populate the FFXM resources for your input textures. If you want to generate the reactive mask using the utility that we provide, you would do the same here, generate the field, populate the reactive description, kick off the work. Same for the dispatch description of ARM-ASR, and finally call dispatch. Piece of cake. If you want to connect things tightly, go for a full tight integration, you might want to keep an eye on this file. So this is the file that contains the actual implementation of the algorithm. So I recommend going to this file, take a look at how things are called, what information you provide, how that data is going to be used internally by the algorithm. And finally, clean things up, just destroy the context, release the memory, job done. So yeah, as I said, if you're going for a tight integration, you have responsibilities. So you'll have to load the shaders and fill some reflection information, but easy. So now, what about Vulkan? Well, I'm gonna quote Tobias on this. Vulkan is hard. So there are things that you want to abstract your users from, all the synchronization, resource management, render passes. And if we were to rely on a tight integration, it would take quite a long time if your engine is not fully prepared. So we decided to speed things up with providing the quick setup by using this standalone Vulkan backend approach that I was talking about. So if you are going to use this approach, we now provide a shader there that you can use for pre-compiling and serializing your shaders that will be used at runtime. We extended things a bit because we liked using DXC compilers. Shaders can optionally use the BK bindings for selecting where you want to bind the resources. But in terms of how you initialize things, just call these functions. There's the first function to request how much memory do I have to allocate for the scratch buffer. And then second function for filling the interface with the relevant function pointers with all the callbacks for the Vulkan code. When filling the resources, just before you are upscaling, you will have to provide the Vulkan handles as well. And lastly, when you are filling the dispatch description before upscaling, the only extra thing here is that similarly you have to provide the Vulkan handle for the command buffers. But a part of that is the process that I was describing earlier. So yeah, some fun stuff. Modern Vulkan. So our shaders, by default in the standalone backend, will try to use the explicit types. Thought that, yeah, modern Vulkan or devices nowadays, there's a lot of wide coverage for 16-bit arithmetic. So I thought, why not? But in any case, we have some macros in the shader that you can use for disabling the explicit types if you want to just fall back to the traditional relaxed precision. In my case, I decided to go for the explicit types because I work for ARM. I have access to the cool internal tools like the shader disassembly. So that gave me good mechanism to identify exactly where the register spilling and these problematic areas were happening. So I could have full control and micro-optimize the shader logic to get rid of every single byte of spilling. Now, the other one is the subgroups. So if you've used AMD's SPD pass for doing reductions, so they use quad subgroup operations for their reduction. And yeah, this is pretty much the same case for us. The compute luminance pass at the beginning of the algorithm that is used later for some heuristics uses this as well. But if you are targeting older devices that might not have support for this, you can use that macro for disabling the use of these operations. And it will still work, it will still be efficient, but the optimal path will be using these operations. And I wanted to use this opportunity to raise awareness of this because it is a fairly common problem in the industry. As we see more and more console-like techniques being migrated to mobile, we keep finding all the time techniques that might be using subgroup operations for things like tile reduction. And a challenge here is that a lot of these times, some assumptions are made in terms of what the warp size or subgroup size is for the platforms. I think the common problem here is that developers seem to generalize the fact that most of platforms will have at least 32 threads per subgroup. In Mali, nowadays, this is not the case. We have 16 threads per subgroup. So if you make that assumption, chances are your algorithm will break and you will start getting visual artifacts, and probably you won't have an idea of why the hell is my code breaking and why is it not working. So just so you know, as I said, it's not the case for our case because we are using quad operations. But if you have that, please double check, try to generalize things. And I don't know, this is a recurrent problem. So it would be really nice if we could sort out this situation in a transparent manner from game developers so they didn't have to create specialized variants of the shaders. And yeah, some conclusions. And it's been a journey. I had a lot of fun doing this. And yeah, in the end, we managed to provide something that simplified the learning curve when adopting our technique. since it's, in essence, FSR2 optimized for mobile and tweaked a bit. ARM ASR became a platform and API agnostic, abstracting the user from any kind of implementation details. And yeah, you can run it everywhere, any API, any platform, as long as the performance allows. And as I said, we provided 2 paths for integrations, a quick one using Vulkan as a target, and slower but more flexible one going for a full tight integration with your engine. And in any case, we succeeded in abstracting developers from how the algorithm works. And yeah, so quick one on this. So you might have heard about the ARM ASR Experience Kit. So this is coming fairly soon, and we will provide all the source code, tutorials, plugins for the commercial engines, and yeah, documentation in general for it. And all of this will be open source, fully under MIT for the entire community to benefit from.
Hey, I don't have a question, but I just wanted to do a shout out to you guys. Thanks a lot for doing all the heavy lifting, because even though we are not specifically targeting ARM hardware, we were like one of the early adopters for Chaos Enscape, because we had like the same problem with low-end PC hardware, like Intel integrated GPUs. FSR2 was running terribly slow. Like it was slower than rendering in just native resolution for us. And yeah, we were seeing good results so far. It's not shipped yet, or it's not production ready yet, but yeah, the first results look really promising. So thank you guys for doing all the heavy lifting.
You're welcome.
Any other questions? Oh, yeah.
So you said you moved most of it over to a bunch of it over to fragment shaders. Are you able to use submask pass merging or dynamic rendering local read or something like that to be able to avoid some of the spilling by doing that? Or is it just that it's more efficient to dispatch fragment shaders?
When you go to Mali, we have this thing called ARM frame buffer compression that nowadays you can only use on fragment shaders. So there are some caveats there, but in essence, if you create your textures with the storage flag to be used as a UAV in compute dispatch, then that won't benefit from AVC. And AVC is great. You get, as an average, 50% reduction in your bandwidth for that particular resource. So please use it. You will get massive wins in bandwidth.
That also explains some of the win on Intel. They have the same problem.
Any other questions? If not, we'd like to thank our speaker again, and then we'll take a break.